There we go. All right, so it should be up in about 8 more seconds. All right, so getting back to here, well, I did document all of this, so even though it was not, even the spoken part is not, recorded, I think you can still follow the reasoning. All right, so there are two ways to proceed at this point. You can either use the 3, which is E2, to move the binary point 3 places to the right-hand side. You go like 1, 2, 3, let's put the point over here, and then figure out what that is representing. Or you can figure out what this is representing and then multiply that by 8. Okay? The choice is kind of yours. Okay? They're equivalent. It's just, are you comfortable working with small fractions of 2, or are you more comfortable working with larger powers of 2? Okay? That's kind of the trade-off. Okay? So I'm going to work out, I'm going to use the bit shifting method. So I look at this 3 here, and I say I can shift the 3 decimal point 3 times to the right-hand side. Okay? So that means the value we are representing is 1 point, not 1 point, okay, because that point has moved. It's 1001.1 in base 2 times 2 to the power of 0 at this point, because I have used up the exponent of 2 to shift the binary point. So there are no more powers of 2 anymore. Is that okay? Because what it used to be, okay, so the value used to be 1.0011 times 2 to the power of 3. So I just decided instead of multiplying by 8, I can shift the binary point to the right-hand side 3 times. Okay, it accomplishes exactly the same thing. We talked about this last time, okay, because the role of each digit has changed. What used to represent what used to represent a 1 is now representing an 8. Okay, so that's kind of why this works out. So now we can just work out this number here. So we got an 8 plus a 1 plus a half times basically times 1. So I don't even bother with the other part. So now we have 9.5 in base 10. Yep.
And this is a negative value, correct, because of the sign bit?
Yes. So the actual value is negative 9.5 is the represented value. Correct. Thank you. So do we have any questions about this process? Yep.
In the hexadecimal term,
Mm-hmm.
what's the 0x in the beginning?
So the 0x is how your C compiler knows that you're about to specify a hexadecimal number. So you can look at the 0x as kind of like a destination of, okay, what follows are hexadecimal digits. C and C++ recognize this prefix as well. So anytime you want to use hexadecimal numbers in C and C++, you just prefix the digits with 0x. And I believe this is also used by most modern programming languages, perhaps even Python. So are we good so far? Okay. So I'm going to leave it up to you guys to verify this, okay? Because I showed you a process last time, okay, how to use a very simple program, ngdb, to look at a bit pattern and say, I want to change the interpretation of the bit pattern so that we are now looking at it as a double precision floating point number, and what is the value represented as a double. So this time we just have to kind of do it in an opposite way. Okay, we put the hexadecimal digits into an unsigned integer, and then we have to interpret it using the floating point method, and it should give us back negative 9.5 exactly. Okay, so I will leave it up to you guys to give that a try, because the more you kind of practice, the more you will understand the concepts. At least that's the general idea. So are we still good here, or do we have any questions about this process? Yep.
One more time, what is the 8 component tell us again?
So the E component is the biased exponent of 2. And instead of using a signed representation, because we want the exponent of 2 to go positive and negative. And the way that IEEE decided to do it is to use a biased representation. So that means if the E's are all zeros, that means the actual exponent of 2 is negative 1023, because it's offset by 1023. Okay? So I'm going to pass the row sheet right now. Here you go. Just initial next to your name. If you are not on the roster, it's probably a serious thing. I know one person who's not on roster for some reason, and that person contacted me already. But if you're not that person and you're not on roster, you really need to let me know so that we can get it handled as quickly as possible. Okay? All right. So do we still have any questions about this, or are we okay with this? Yep, go ahead.
So the unshifted version, the times 2 to the third version,
Mm-hmm.
you would just do the same process, but then multiply the
Yeah.
result by 8 to get the solution of it?
Yes. So this is 1 plus the, okay, so let's figure out. There's no half, there are no quarters, there's 1/8, right? This is a 1/8. So it's 1 plus 1/8, and then we have a 1/16. So all of this added together is really just this portion, right? So, and then we multiply this by 2 to the power of 3, which is 8. So when you look at that number, which is 1 in parentheses, 1 plus 1/8 plus 1/16, so that would be 1 and 3/16, right? And when you multiply that by 8, we should get the same thing, which is 9.5. Yeah, that looks fine. Yeah, we should get 9.5. Is that okay? Yeah. Yeah. So you can either move the binary point, by using the exponent of 2, which is kind of what I preferred, or you can just work out what the mantissa is, which is in this case 1 and 3/16, and then multiply the mantissa by the power of 2, should get to the same answer. Are we good? All right. So what we'll do next, okay, going back to our notes, the rest of this really has to do with conversion. In other words, if I give you a base 10 mantissa, if I give you a base 10 scientific notation, how do you translate that into base 2 double precision floating point representation? That is something that you normally do not think about, because even in C and C++, if your program needs to read in, let's say, pi or something that is what we know of as an irrational number, you just go C in greater than, and as long as the variable on the other side is a double, it handles it for you, right? So what we're going to do is to look into the logic of that manipulation. Okay? If you are given a base 10 scientific notation, how do we convert that into the actual base 2 representation as a double? Are we doing okay so far? Because in that process, we'll understand quite a few things about how we represent values and also how we convert values. Okay? So that's basically what section 5 is about, converting from base 10 scientific notation to double. But before we get there, we're going to look at this mess here. Let me highlight here which part I'm talking about. And we'll try to figure out what this means. Okay? It is actually important. Just this gibberish is actually important. Okay? It is called a regular expression. Has anyone heard of regular expression before? Okay, excellent. We got a few people. And what do we normally use regular expressions for?
Pattern matching.
Say again?
Pattern matching.
Pattern matching? Yep.
I was going to say like string parsing.
String parsing. So you can see whether a string fits a pattern or not, right? So that's one way to use it, is to say, okay, if I give you this string, I give you this regular expression, is it recognized? Does it fit this description? Okay? So it's really quite useful. Okay, in programming, regular expressions are very useful for validation. Okay, if somebody is supposed to put in a zip code, okay, how do you check the syntax of a zip code? If somebody is to put in a phone number or a social security number, how do you check whether it has the right number of digits? Or if you want to have dashes and parentheses and whatnot, are they at the right places? Okay. Now you can certainly write your kind of custom logic to do it, right? You can do and you can scan through the array, use a whole lot of loops, conditional statements, and whatnot to specify the same logic. But this is a lot easier, and you guys will say, no, this is a lot harder. Well, it's only a lot harder because you have not been exposed to it. If you have worked with this for a while, it would be kind of second nature, okay, for you to figure out, okay, this kind of syntax requires this regular expression to express it. Okay? For those of you who have watched the movie, The Imitation Game, okay, and what is that movie about? Who is the main character? Which historical person is the main character of that movie? Alan Turing, okay? And what is his contribution in World War II? Not Turing Machine. He was responsible for not quite hacking, but he invented a machine or co-invented a machine to decipher messages that were encrypted using the Enigma machine. So that was his contribution. So now the question is, what does that have anything to do with regular expression in an assembly language programming class? Right? I mean, those things seem to be disconnected, have no continuity whatsoever. They don't seem to be related. So does anyone want to kind of, connect the dots?
The purpose of the machine that he encoded was to decipher the coded messages that the Germans sent out.
Yes.
So it needed to recognize patterns.
Now, what pattern were they recognizing? So, okay, so imagine you're Alan Turing, okay? So you're given this problem, okay? Because the transmission is radio wave, so that means it's a multi-drop type of topology. The transmitter cannot say, okay, I'm going to go for a narrow beam and only these people can receive the physical signal. No, everybody gets the signal, okay? Your people and the enemies, they all get a signal. But because the enemy does not have an Enigma machine, they cannot decrypt the message. So all they can see are basically gibberish. So the question now is, how can you go back and figure out what was the configuration of the Enigma machine that was used to encrypt the message? Because the encryption key is also the decryption key in this particular case. It's symmetric. So the question is, how do you figure out which combination? Okay, I think at the end, there were 5 disks in the Enigma machine to do all the kind of rewiring to map characters to other characters. Okay, so the question is, how do I know the configuration? So does anyone know the answer to that? What was the clue? They were doing it by hand at first, but when the last disk was added, it became intractable, when you do it manually. So as it turns out, a lot of the, go ahead.
Didn't one of the part of the transmission require something very specific, like some sort of
Salutation.
salutation or
Yep.
something about along with the weather report on there, so they can match the which day or
Right. So there were specific patterns that they were looking for, right? In a transmission. So if you think you got the right key, then the decrypted message should contain these specific things. Okay? So it could be a salutation to Hitler, okay? It could be the date of the day, and so on and so forth. There were certain patterns that can be expected in the communication. Is that okay? And then Alan Turing's theory is basically just that. Okay, he was building a machine to recognize what he calls a language. Okay, which is nothing more than just going like, do I see Hitler? Okay, in this message. Okay, if so, then if I see Hitler after going through all the decryption, then I'm good. Okay, this is the right machine for today's encryption. Are we doing okay so far? So he basically abstracted the entire concept, and he called the abstracted machine, it's called a finite state machine, FSM, or it's also known as an automata. Okay? Most of you, if you're in computer science, you will encounter those concepts again as an upper division class in undergraduate. Okay? So you will encounter all of these things again. But that's how regular expression was kind of invented. Okay? We call it regular expression, but all it really is a classification of language that can be recognized by a finite state machine. That's it. Okay? Now, there are finite state machines, there are stack machines, and then there are Turing machines. So there are different classifications of these machines based on can they store something. Okay? Now, finite state machine cannot store anything. All they can do is to know what is my current state. Okay? And then you throw an input symbol to it, and it goes like, okay, I can now transition from one state to another state. So that's kind of the limitation of finite state machine. But without any type of storage, it cannot process anything that has parentheses. Okay? So nesting, as it turns out, requires the concept of a stack. And that's why there are stack machines. Okay? So stack machines are basically finite state machines, but with a stack as storage. And those machines can recognize basically all programming languages. Because all programming languages that we use today, they're all recognizable by stack machines. So for those of you who are interested in compilers, okay, you will get back to finite state machines. You'll get to stack machines and then figure out the relationship between, okay, this is the C syntax. What kind of a stack machine recognizes C syntax? Okay? The last, which is the most powerful class of machines, is called a Turing machine. And the Turing machine basically has a tape instead of a stack. So a tape is different from a stack in the sense that it is not last in, first out. It's quote-unquote random access. You can go to any position of the tape, read a symbol, go to any other location of the tape, read another symbol, and use that to determine how to perform the state transitions. Now you might say, well, if it's a single tape, doesn't sound like it is very powerful. As it turns out, with one single tape, you can emulate multiple tapes, you can emulate a lot of things. So you will get to those concepts later. So what we are looking at here, which is regular expression, is really just the most simple machines. Okay? Just a finite state machine can recognize this. So we'll go ahead and see, okay, what is this really specifying? The square brackets without any backslash in front, they enclose alternatives. So in this case, plus minus are alternatives, but not only are they alternatives, they are also optional. The optional part is specified by backslash equal to. So backslash equal to basically says whatever is immediately before me can occur 0 or 1 time. Okay? Well, what is right before the backslash equal to? Square bracket plus minus, which means plus or minus. Okay? So that means plus or minus can occur 0 or 1 time at the very, very beginning of a base 10 scientific notation that I have chosen to use in this example. We good? Okay? So what is after that? After that is a backslash D. So what does that mean, backslash D? Backslash D simply means it's a base 10 digit. It can be 0, 1, all the way up to 9. Okay? And then we have a backslash open paren. Backslash open paren and backslash close paren are used for grouping purposes. Look at those as open brace and close brace in C++ programming. They form a block. So they can consider the entire block as one thing. Is that okay? So now we want to see what is in this block here. Well, this block has a backslash dot. A backslash dot is a simple dot. Okay? The reason why it has a backslash in front of it is because a single dot has a special meaning in regular expression. Okay? So in order to escape the special meaning, we put a backslash in front of it. So backslash dot is really just our decimal point. We see backslash D again, which is a base 10 digit, but this time it has got an asterisk after that. So any number of, very good. So an asterisk means any occurrences of, including 0. So that means you do not even need to have a digit after a decimal point. Okay? According to this, it can be 0 occurrence or any other number of occurrences. So that means the point blah, 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 this entire thing is in its own block. Okay? This is the opening of that block, and this is the end of the entire block. Exactly. So the decimal point and everything to the right-hand side of the decimal point of the mantissa, they're all optional. So 1 can be recognized as a number. 1.23 is also can be recognized as a number. Just 1 point without the 2, 3 is also a number. It is still recognized. Are we still doing okay so far with this interpretation? Okay. Yeah. Mm-hmm.
That means because you have to have a digit?
Yes. This digit is mandatory.
Yeah.
But this digit and any number of this digit is, it has to follow the dot. But the entire thing, the dot and also all the digits to the right-hand side of the dot, the entire thing is optional because of this backslash equal to. Because the backslash equal to applies to whatever thing is right before that, and whatever thing is right before that turns out to be this entire block. Are we good? All right. Okay, so what goes after this? Well, we have a backslash open paren again. So we automatically look for the end because we want to know what is the extent of the block. So the extent of this block is all the way over here, which means everything in here, okay, I'm just highlighting the stuff that is inside the block, applies the backslash equal to at the very end applies to this entire block. So what is in this block? Well, this block starts with an E, a lowercase e. So most letters are literal, okay? So that means the E has to be here, has to be in this block. And then it's followed by, the selection plus minus, choose one. Or none, because the backslash equal to, once again, applies to the square bracket plus minus, which means if you want to, you can choose one of the two, but if you don't want to have any sign, which is implicitly a plus, you can leave the sign out entirely. And then what is after that is, once again, the backslash d, which is a digit from 0 to 9. And at this time, we see another new quantifier, which is backslash plus. That means at least one occurrence. Cannot be 0, okay? At least 1. Correct. All it says is at least 1. Okay? So now we look at this entire block, starting from here and all the way ending here. And this entire block is followed by backslash equal to again, which means the part that specifies the exponent is also optional. So 1.23E0 is good, okay? But 1.23 by itself is good too, okay? But 1.23E is not good, because if you have an E, you better have at least one digit after it. Are we doing okay so far with the interpretation of this syntax? Okay? Yep. Yes. Okay, let me answer his question first, and then we can use an example. Go ahead.
Which part of that dictates that you have to have a number if you have to E?
The fact that, okay, so E is here.
Right.
This part is optional.
Right.
This part here says you have to have at least one digit. And that's why after the E, you can ignore the sign of the exponent, but you have to have at least one digit after the E. And then there was another request for an example. So what kind of example are we talking about? An example of how this works, or an example of what this can recognize? Of what you can recognize? Okay. So I think I got a perfect tool for this. Okay. So we'll go ahead and use VI, and then we'll enter a few numbers. Okay, we'll enter some numbers that should work and some numbers that should not work. Okay, so I'll enter like 0.23, which most people would say, yeah, that looks like a legitimate number to me. Okay, we'll have 110.23. We'll have 10 point. Okay, we'll have 1.23. We'll have 1.23 E, 40. We'll have, let me turn off spell check. We'll have 1.23E without the additional number. We'll have 1.23E plus 2. We'll have just 1 point, and then E4. Okay? So all of these are kind of examples of what we normally recognize as numbers. Okay? But which one passes the test and which one does not pass the test? Okay? So I'm going to test it using VI. Okay, VI stands for, okay, does anyone know what is the meaning of VI? Some of you have heard of the editor called VI and probably have heard of the steep learning curve of VI. But what does VI represent? Why is it called VI? You laugh at this once you learn the reason why it's called VI. It stands for visual. Because before VI, there's only ed, and ed is a line editor, which means you can only edit a text file one line at a time, which is not very visual. VI itself is screen-based. It gives you a whole screen, so it's visual. You can move the cursor up and down. That was considered big-time visual back in those days. And these days, when you guys think of visual, it's like, is it 3D in virtual reality? That's kind of visual. No, back in those days, this is already quite visual. So now you know a little bit of things of computing history that you did not know before. That's what's nice about having an older professor in the class. You learn a lot of things that really does not matter. Okay. So in VI, the nice thing is this syntax is actually what VI recognizes. So I can use a slash, and then I specify exactly that syntax. I cannot copy and paste, unfortunately, because the encoding that you see in the HTML editor is not translating well back into what VI recognizes. So some of the characters is not what it seems. Okay? So I have to actually hand enter this entire thing. That wasn't too bad. So this is, it's recognizing one thing at a time. It's not looking at a whole line here. So right here is recognizing the 13, the 23 as a number, and then it's recognizing the 2 and then the 3. It's doing the laziest recognition. It's looking for the shortest string that matches. I think there's a switch to look for the longest string that matches. I cannot remember how to turn on that feature. But basically, this does work. Okay, this regular expression stuff works in VI. So VI is capable of searching for things based on regular expression. There's a switch to do it to look for the longest match, but I cannot remember. Yep.
Can't you put like a carrot at the beginning?
Yes, I can. Good idea. Yep. Okay, so let me copy. I can copy and paste this. So we'll copy this, and then we'll do a caret. So a caret means at the beginning of a line, and then I'll do a paste, which is what we had, and then a $sign means the end of a line. So this means I'm restricting the match pattern now. It has to start at the very beginning of a line, and it has to end at the very end of a single line. Okay. So now the first match, okay, I didn't look at the beginning here. Do you see how it went to, okay, let me turn on line numbers. It skipped lines 1 to 4 because none of those match. And then line 5 is the first number that matches, 1.23. The next match is the next line, which is okay because I just specify an exponent component, which is optional. Line 7 does not match because the E is supposed to have some digits after that, at least one, and there's none in this case. And it matches that one, it did not match, line 9 matches 2. So this is kind of a cool way to kind of see how the regular expression stuff works. Yep.
So the reason why you cannot recognize first three because each one of them doesn't have the first digit in front?
It doesn't have a single first digit before the dot. Now, 0 point it will recognize because 0 point is still a \d, but it would not be a normalized mantissa in that case because we want the normalized mantissa to have at least one. So technically, I need to change the first \d to only contain 1 to 9 and excluding 0. Mm-hmm. So are we good so far? All right. Now, if I give you a number, okay, so I'm going to close this and kind of get rid of that for now. So if I give you a number in base 10 and it does fit this particular description here, how do you write your logic to recognize that thing, and how would you represent the base 10 scientific notation but only using integer types? Okay, I'll give you an example. Okay, for instance, let me go back to Notepad here. If I give you this number, negative 1.23e, let's make this fun, negative 23, okay? And I say you can represent, you have to be able to parse this and only represent it using integers, okay? You can use signed integers, okay? Signed or unsigned integers. How would you do that? And the hint is, don't even think of using a single integer to do it, okay? Think of a structure or think of a class, okay? If you are allowed to define a class where the members of the class can represent all the components that we have here, but you're restricted to the use of only integers, how would you do it? Well, the mantissa, yeah, go ahead. Oops. It's going to come back. Yep. Okay, go ahead.
So for sure the class that gives the integer that gives the power.
The exponent,
One for sure we're given the sign.
Okay.
And probably the number, just the number, like 1.23, we're going to keep 123.
Yep, exactly. So if you keep it,
By 10.
right, so we can use one integer for the sign, right? We can use another integer for the mantissa. Well, this one can be unsigned now because the sign is already taken care of using another member. So we have an unsigned for the mantissa, and then we have a integer signed integer for the exponent. Does that make sense? Yeah.
So, is there a particular reason to use an unsigned integer for the mantissa and have a separate integer for the sign, rather than just using a signed integer for the mantissa?
Yes, because the sign really is not that important in the conversion process. So we want to make the mantissa basically just non-negative, so that the logic doesn't have to deal with the sign of the mantissa. So that's the only reason.
My other question.
Uh-huh.
Do we have, so because you could input different, with different, yeah, you could input values with decimals in different relative positions.
Mm-hmm.
Do you also want to have something to track where that decimal point is?
You don't have to. Okay, so let me describe how I would do this. So the number that we just look at here, sign is going to be a 1 or non-zero, to indicate that it has a sign bit of non-zero. The mantissa, in this case, I would use 123 for the mantissa. And then the exponent is going to compensate for messing around with the decimal point, okay? Because in order to go from 1.23 to 123, I have, the mantissa is now 100 times what it used to be, right? But I can adjust the exponent to do that, exactly. So the exponent is negative 23 minus 2, which is negative 25. Because negative 1 times 123 e negative 25 is the same as negative 1.23 e negative 23. Is that okay? All right. So this is how we're going to do it. Okay, is basically look at the mantissa and go like, yeah, you can have as many places as we want to the right-hand side of the point. We'll just keep shifting it until it becomes an integer. All right? But wait, because of all this shifting, the mantissa is now a lot bigger than what it's supposed to be. But that's okay, because we can adjust the exponent or the power of 10 in order to compensate for all that shifting. So are we doing okay so far with the method of getting this done? Are we good? So how many of you would like to have this as your homework assignment? None of you. Of 2. Okay, we have a single digit of people wanting it. So you can do it if you want to. Okay, you can replace the module that I have in today's lab. Or, well, actually, the next lab is going to have it. But I will give you, the code to do this. Okay. So if you want to do it yourself, that's fine too. But I will supply the code that will do the parsing already. This is not the hard part. I'm giving it to you. The hard part is, once I have this, okay, once I have the mantissa, I have the power of 10, okay, and the sign is actually not really important. How do I convert this into base 2? In other words, how do I start from here, starting from this representation? Then how do I convert it into a base 2 double precision floating point number representation, but without using any double functions, without using any double types in the process? So I'm going to stick with only integer math, integer arithmetics, and just addition, subtraction, multiplication, and division, and also comparison. Only using those, and bit shifting if you want to, only using those, how do I convert a representation like this, which is pretty easy to do. Okay, give me a string in base 10 scientific notation. I can get to this relatively quickly. But from here, I want to convert it into the 64-bit double precision floating point number. The question is, okay, how do we get it done? What do you think? Yep.
Look, first one would be taking both the sign and mantissa, converting those into binary. The sign is easy because it's either 0 or 1.
Yeah, the sign is not a problem. So we basically leave the sign out until we have to reassemble everything. We just go, okay, is the sign non-zero? Yep, put a 1 over there in bit 63. Done. It's the rest of it that is kind of like, how do we do this?
Mantissa, you can use the formula you previously learned a couple weeks ago, converting it into base 2 for finding the digits.
So we have to do it step by step, okay? So we will go through this, step by step. And the first thing I'm gonna do is to turn on Zernal, because some of this I can write it using Notepad, but it doesn't look right, okay? So I'm gonna use Zernal, because this will make the math equations look better. Okay. All right, so let's go ahead and start with this. So we know what the value is, okay? Because we have all the components at this point. So we'll just use M to represent the mantissa. And there's only one mantissa, okay? There's only one mantissa, which currently is in base 10, okay? 123 is kind of base 10, okay? And then we'll say we have one power in base 10. Okay, we'll call this E10, okay, which is the exponent in base 10. Is that okay? And then we have another component here, which is 2 to the power of e2, which is the power of 2. Are we good so far? Okay. So in our example, right now, what we have is the mantissa is 123 as a value. Now remember, 123 is only one way to say out what the value is. Okay? I can just as easily right now and say that 123 is in base 2. Okay, I have to think a little bit because there's a whole bunch of ones. I have to find out exactly where to put a 0 when I say it. So it would be 1, 1, 1, 1, 0, 1, 1. Did you guys get that? Okay, 1, 1, 1, 1, 0, 1, 1 in base 2. So right now, I know, what m should look like as a binary number. That is not the problem, okay? M is not the problem because I can look at it as a binary number anytime I want to. So how did I do this conversion so quickly? 123 is an easy one to do because 127 is super easy. Why is 127 super easy? Because it's a whole bunch of ones. How many ones are we talking about? If you have 8 ones, you have 255. So you have 7 ones, okay? So if they're all ones, it would have been 127, or what we know of as 127 in base 10. How does 123 relate to 127? They're off by 4. And the good thing is 4 is a power of 2. So you just have to take away 1 power of 2, which is 2 to the power of 2, from 127, and then you get 123. So you have all the bits on, as all 7 bits on, and you just go like, okay, which one of you is responsible for that 4 that I don't want? This guy just go like, I am. Well, you're 0 now. Then we get 123. Is that okay? So there are certain numbers where you can apply tricks, okay, to get to the binary representation really fast. 123 turns out to be one of them. Okay. So the m is not a problem. The problem is our E10 is non-zero right now. Our E10 is negative 25. That is the problem. Are we good? What about the E2? Well, E2 right now is a 0 because we have not started the process. There are no exponents of 2 right now because we haven't started the process. The only exponent is in base 10, and we know it is negative 25 because of the reasoning that we have done earlier. Are we doing okay so far? Okay. So what we want to do is to say, go through some magical process here, okay? I don't care what m ends up to be, blah, blah, blah. I want E10 to eventually become 0. And I also don't really care what E2 will turn out to be because a lot of things can be done to adjust between m and E2. Okay? We can move the bits around and increment and decrement E2. So that's not the issue. The issue is I need E10 to go down to 0, or to go up to 0 in this case because it started negative. Are we doing okay so far with the reasoning so far? So how do you get rid of a power of 10? How do you get from negative 25 to negative 24? You have to, okay, so if you move E10 from negative 25 to negative 24, the represented quantity is going to be 10 times what it used to be, right? But I don't want the value to change, so what do you need to do? What do you have to do the mantissa when you add 1 to E10? You have to move the decimal point, but in which direction? To the left or to the right? You have to move it to the left. Okay? So let me write it down. Okay? E10 plus plus means move decimal point to the left. But that's no good, because that means 123 or 123 becomes 12.3. And I explicitly said no double in the calculation process. I cannot just drop the 0.3 either, because that means eventually you get, if you try to shift it 25 times, what do you get? You get 0, okay? If you shift it 3 times, you get 0 already, let alone 25 times. So we know that method does not work, okay? So what do we need to do instead? I need to decrease E2 to make the mantissa large. Okay, you guys are all looking at me go like, what? What are we talking about? Okay, so what we do is we say 123 times 10 to the power of negative 25 times 2 to the power of 0. What is it equal to? Well, it turns out to equal to 246 times 10 to the power of negative 125 times 2 to the power of negative 1. Does anyone want to argue with me that, no, that equality doesn't hold? No? Okay. Because if anyone wants to do that, I'm going to recommend that person to take remedial math. Okay? All right? So I can do this again, right? I can multiply everything by 2 again. So I can say, well, what about this? 492 times 10 to the power of negative 25 times 2 to the power of negative 2. Would that work? Yes? All right. So how far can I go? In other words, how much can I multiply the mantissa by 2 until go like, hold on a second here. Can't do it anymore. What do you think? Let me ask the question again. How many times can I multiply the mantissa, or how many times can I double the mantissa and just go like, well, I can keep doubling the mantissa because I have this exponent of 2 that I can keep decrementing to make up for the doubling of the mantissa. But what is the limit? When do I say, okay, can't do it anymore, got to stop? The answer is a lot. The answer is a lot. Okay, what is a lot? Remember, this you have to implement it in C at some point. Yes? When you run out of bits to represent it. Okay. So we want this all the way until m is less than 2 to the power of 64, the whole thing minus 1. And we want the maximum m that is less than 2 to the power, less than or equal to, less than or equal to the power, 2 to the power of 64 minus 1. Now that is a huge number, but it doesn't take me a long time to get there, because every single time I double, I am getting one step closer to it, okay? In the worst case, okay, if m was 1 to begin with, in 63 doubles, I would have gotten to this point. Does that make sense? So it doesn't take a lot of iterations. If I set it up a loop, it doesn't take a whole lot of iterations. So I end up with a huge m, right? Why do you think I want to get an m that is like really, really huge? Yep. So I can now finally, I can divide the mantissa by 10 without worrying that I'm going to lose a lot of precision, okay? So what I'm going to do at this point is I'm going to say, well, let's m be m divided by 10, okay? And at the same time, I would do a let's see, I will increment E10 in this case, right? Oh, if we're incrementing E10, that means we're going from negative 25 to now negative 24. We got one step closer to where we want. So that means I can just reapply this method over and over and over again, and eventually I will get there. Does that make sense? So I make my mantissa as large as possible by doubling. When I cannot make it bigger, any bigger, then I divide the mantissa by 10. Every time I divide the mantissa by 10, I increment the exponent of 10 by 1, and I keep doing this until E10 equals to 0. Okay, that is the center. That's basically the heart of this conversion process. Okay, this is the logic to do it. But then we still have some minor issues we have to deal with. Okay, so now we look at everything from the C perspective. This is not entirely right, because when we store m divided by 10 into m, which is an unsigned integer, we are losing something, right? Because integer division automatically truncates. In other words, if you have 123 and you divide it by 10, what do you get? You get 12, not 12.3, because the 0.3 is lost. It is truncated. What about 129 divided by 10? What do you get? You also get 12. Then you go like, well, wait, hold on a second here. 12.9 is closer to 13. Maybe we should use 13. It doesn't do rounding. Okay? C does not automatically do rounding. It automatically truncates when you have integer division. Okay? So that is not good. Yep, go ahead.
Is this where floating point errors come in?
Not quite.
Okay.
Not quite. So every time we do this once, we lose something, okay? And m always ends up a little bit smaller than what it's supposed to be. Not a whole lot, right? Because remember, m is one of the largest values you can represent using 64 bits, but you're still losing something. But if I do this like 25 times this, in this particular example, those errors are all leaning in one direction. Each step makes the answer, it introduces error. Okay, that's inevitable. Okay, but the error is always on one side. It is always making the result smaller than what it is supposed to be. So this is what we say a bias. Okay, we say the error has a bias. It is always leaning on one side. So if you do any type of repetitive operation and there's an error and the error is biased, then you have a problem. Because when you perform those iterations more and more times, the error always grows in one direction. So you end up with a value that is off by quite a bit when you're all done with the process. So we don't want that, okay? And the problem has to do with truncation. We don't want truncation, we want rounding. Okay? Then you go like, well, that's pretty easy to round. I mean, you can just compare the result. If it's closer, if it's less than 0.5, we round down, and if it's more than 0.5, we round up. But remember, I said no double calculations, right? No double arithmetics, no double comparison, no doubles whatsoever. So how do we do rounding without using doubles? You can use modulus. You don't even need to use modulus. Yep.
If you're going to divide by 10, whatever the least significant digit is,
Mm-hmm.
turn into a fractional value. If that digit is less than 5, you can round down. This is before you divide. If it's greater than 5, you can push up, round up.
Well, the first thing we ask is this the same thing as taking the floor of x plus 0.5? Okay? What do you think? Well, we'll try a few times, right? So we'll say, what is the rounded value of 0 itself, okay? Does it equal to the floor of 0.5? What do you think? Yeah, okay, that works out. Because the floor of 0.5 is just 0. Does everybody know what is floor? Okay. The floor is the largest integer that is less than or equal to whatever number you're taking the floor of. Okay? So let's try something that is fractional. Okay? 1.1. Okay? The question is, does the rounded version of 1.1, does it equal to the floor of 1.6? Yep. Okay, seems to work. What about the rounded version of 2.5? Okay. Does it equal to the floor of 3? Yes. So we can do x plus 0.5 and then take the floor. That becomes the same thing as rounding. But then someone's going to complain and go like, but 0.5 is a double. It is not an integer. You're absolutely right. Okay? But turns out the only time we need to round is when we have division. Okay? So what we want to do is to say we want to calculate the rounding of some mantissa divided by 10. Okay? So in this particular instance, we only need rounding when we want to apply rounding to the it's not the quotient, because quotient is an integer, to the result of m divided by 10. Okay? So now we look at this and go like, okay, we can use the other thing and say this is the same thing as m divided by 10 plus 0.5, right? But we don't want to do 0.5. So we look at this and we go through some math stuff. Okay? And we go like, Yes? Are we all in agreement here? Okay. But wait, the floor of m plus 5, the whole thing divided by 10, is done automatically in integer math. M plus 5, the whole thing divided by 10, that division is an integer division. It automatically does the floor thing, which is, so that means I don't have to do any math in double in order to do rounding. All I have to do is to add 5 before I divide it by 10. Is that okay? That's pretty cool, right? So now we have a way to do rounding to get rid of the bias. Now you might say, but this still has errors because we still eventually end up losing a digit. You're correct. We're still losing precision. We still have errors. But the error is no longer biased. Sometimes it's leaning this side, other times it's leaning the other side. So except for very, very weird cases, okay, it would just kind of jitter around a little bit, but it won't go all the way to one side or the other, okay, which is good. Okay, this is as good as it can get, basically. So are we good so far with all of this stuff here? So what is the process? The process is make m as large as possible. Okay, make it the largest, double it until it barely fits in a 64-bit unsigned integer. Then you add 5 to it, divide it by 10. That becomes the new mantissa. But every time you divide the mantissa by 10, you can add 1 to the exponent of 10. Okay? But after you divide the mantissa by 10, guess what? It's no longer the largest mantissa that will fit within 64 bits. So what do? Keep doubling it until it is no longer, until it's the last value that can still be contained within 64 bits. Then you do the whole thing again. So you basically do this entire thing until E10 is 0. So what you would normally end up with is a gigantic mantissa. Okay, it probably will. You can make it fit all 64 bits, and a pretty negative E2. The exponent of 2 will be kind of negative, because guess what? It is absorbing all of the original E10 plus the mantissa being large. So it's going to be pretty negative. Okay, your E2 is going to be pretty negative. That is basically as far as we'll take it in this class, because the rest is really just shifting things around a little bit, adding a displacement to the E2, putting all the bits in the right places into a double. That's boring stuff. Okay, this is the fun stuff. So as it turns out, are we running out of time? Yeah, just about. So as it turns out, my implementation of this logic is actually more precise than cin. when it's reading base 10 numbers. Just by a smidgen, just by a little bit, but it is slightly more precise, using this method. I don't know internally what the C library, how it converts the numbers, but this method turns out to be actually very accurate. All right, so we do have a lab tonight. I'm gonna set it up, in the lab. I do need the row sheet to be passed back to me. Okay, so if you don't mind, can you walk up here and give it back to me? Okay, that's all right. Thank you. So I'll see you guys over at the lab. And I'm going to stop the recorder first.